Good morning, Year 11. Today we're going to have a look at calculating the energy stored or released from an object as its temperature changes. Before we do that, please make sure you've had a go at the do now and then play the video again once you've completed it to see the answers. Okay, so let's have a look at what we've got. So hopefully we had the equation for kinetic energy as EK is 0.5 times by mass times by speed squared. The equation for gravitational potential, EP, is mass times gravitational field strength times the change in height. If a car has 50,000 joules of potential energy at the top of a slope, how much will it have at the bottom? So in this question we're going to assume that air resistance is negligible and there's no friction. So if you have 50,000 at the top, all that potential energy will be converted into kinetic energy, so you're going to have 50,000 joules of kinetic at the top. How fast will it be travelling? Well, we have to use this equation, so we do 50,000 divided by 0.5 times the mass. That's all square rooted. I'll bang that into a calculator quick. And that gives us 31 meters per second. So 31 meters per second. I tell a lie, I've rounded that incorrectly. It should round to 32 meters per second. So the actual answer was 31.6. I misrounded there. Gravitational field strength at Earth's surface. We need to recall that it's 9.8 newtons per kilogram. Okay, so this is the concept we're going to have a look at today. I want you to first imagine we've got these different materials. So this one is copper, this one is brass, this one is iron or steel, and this one is aluminium. Now, all of these have a mass of exactly 1 kilogram. You'll notice that some of them are very different sizes. So this one's probably the smallest, this is the largest, and that's because the material, the metal that they're made of, metals that they're made of have different densities. That density isn't the only property that's different. These all have a property called their specific heat capacity, and because they have different specific heat capacities, if we supply energy to them, they're going to increase in temperature at different rates. I've highlighted this definition on the bottom over here. So the specific heat capacity of a substance is the amount of energy required to raise the temperature of 1 kilogram of the substance by 1 degree Celsius. So for example, this aluminium might have a specific heat capacity of 900 joules per kilogram per degree Celsius. That means I would have to supply this with 900 joules of energy to increase its temperature by 1 degree Celsius. These all have a mass of 1 kilogram. The equation that we'll use is E is mass times specific heat capacity times the change in temperature. So if we go from temperature 1 to temperature 2, to work out the change in temperature, we would just do the final minus the initial. So this delta symbol, this triangle, just means change in. So for example, if I start off at 10 and I go up to 15 degrees Celsius, my change in temperature is 15 minus 10 is 5 degrees C. This is different for every material, be it water, be it steel, be it brass, anything. Air has its own specific heat capacity. Interestingly, water, which we'll have a look at it in a second, has one of the highest specific heat capacities there is, which means you need lots of energy to increase the temperature of water, which is why it's really good at taking thermal energy away from something. 99% of the time, all you'll have to do is calculate that change in energy. So it will just involve multiplying those three numbers together. It might be a bit confusing because you'll have to calculate a temperature change. Other than that, it should be fine. Sometimes you might have to work out either the mass of substance being heated up, the specific heat capacity itself, or the change in temperature. If you want to use a triangle, this is the one. So we put the energy at the top, mass, specific heat capacity, and the change in temperature. So if you wanted to work out the change in temperature, you'd cover that up with your finger. You'll be left with energy divided by mass times specific heat capacity. And we'll have a look at a few examples of that in a second. Let's have a look at this first example. So a student places 0.5 kilograms of potato, well, that's a mass, into a pan of water. During cooking, the temperature of the potato increases from 20 to 100. So let's do the second temperature minus the initial temperature. 100 minus 20 is 80 degrees C. So the temperature increase, the temperature change, is 80 degrees Celsius. The specific heat capacity of the potato itself is 3,400. That's our C. That was our delta T up here. So as always, we must write the equation every time. So mass times specific heat capacity times the change in temperature. The mass was 0.5. The specific heat capacity we've been given here is 3,400. And the change in temperature, which we worked out a few seconds ago, was 80 degrees Celsius. I'll type that into my calculator. 0.5 times 3,400 times by 80, 136,000 joules. So that is 136. And I'll underline that to show that it's the answer I want the examiner to mark. So remember, every time we're going to do equation, substitute the correct values, being careful of our change in temperature, and we're going to evaluate it. We're going to type it into the calculator, we're going to write the answer, and we're going to put a unit on the end. So we have to do those 5 things every time. This next one, say after the water has boiled, the temperature of water decreases by 22 degrees Celsius. Oh look, they're being nice to us this time. They've given us the change in temperature. So it's a decrease of 22 degrees Celsius. So we don't have to do anything minus anything else for now. That's good. The energy increase, oh, so we've got our E here. That's 46,200, and the mass is 0.5. And we're calculating the specific heat capacity. So we get given change in temperature, energy, mass, and this is missing, so we have to calculate that. We look at our triangle from earlier. So if we cover up the C, we're left with E divided by M times delta T. So C equals E over M delta T. That is 46,200 over 0.5 times 22 degrees. Again, we don't have to do any further calculations here, that's done already. I've not left enough room to lay it out properly. I'll just do it to one side, but when you do this, make sure you leave yourself plenty of space. 46,000 over 0.5 times 22. And before I press equals, I'm looking for something like 4,100, 4,200. So let's hope we've got this correct. And yes, we have. 4,200. And it's the amount of energy joules per kilogram per degrees C. So it takes me 4,200 joules to increase 1 kilogram by 1 degree Celsius. I did make one error in my question here. I need to say that this is a decrease. So the temperature is decreasing because the water's cooling down. It's after we've boiled it. So rather than the temperature increase being 46,200, it was a decrease. So it makes no difference to our answer, but just in case any of you spotted that mistake. We will do another example here. So I've managed to find quite a few examples of these questions from past papers. So we'll have a look at what we've got here. So we get given an energy. We get given a mass. So we've got an E. We've got an M for a mass. We've got a specific heat capacity here. Oh, so it's water, so it's 4,200. We knew that already. We've just calculated it. And it's given us an initial temperature. So initial means the temperature at the start. And we need to calculate the temperature of the water after 2 hours. So we're going to have to calculate our delta T, our change in temperature. And then we're going to have to add that change in temperature or take it away from that initial one. Okay, so it's boiled and it's cooling down. So yeah, we're going to have to take this number away from that. Our equation that we must start off with is MC delta T. If I want to make delta T the subject, and these two have to go underneath. We could have used our triangle, but I'm just going to divide through this time. So E over MC. So our energy was 46,200. Our mass was 0.5. And our specific heat capacity was 4,200. I will type that into my calculator. And the value I get for my change in temperature is 22 degrees Celsius. So that's my temperature change. We're not quite finished yet. We started off with an initial temperature of 100, and we're transferring energy from the water in the kettles to the surroundings. So the temperature of this water is going to go down, it's going to decrease. So I need to look at what I had at the start. So it was 100 degrees at the start. I've cooled it down. So I've lost 22 degrees. That means the temperature is going to be 78 degrees Celsius. And that's what the examiner was going to be looking for. Again, so I've put my rearranged equation. I've substituted in my values. I've calculated the change in temperature. And then I had to do the extra step. I've used my correct unit. I had to do my extra step at the end, taking it away from the initial value. So just be very, very careful that you understand what's happening in the question. So these next 3 or 4 questions are ones that you need to do yourself. I would make sure that I followed these steps every time. So you're going to write the equation, you're going to substitute the values, you're going to calculate the energy change, and you're going to give the unit. So this one's looking for energy transferred. So all you need to do is use your MC delta T, your change in temperature. That should be fine. Next one, we're transferring energy again. Oops, that question is incorrect, so I'll change that before you get there. What you need to do is just calculate the energy needed to increase the temperature of the water of 200 kilograms by 50 degrees C. So again, this is just your energy is MC delta T again, and you just need to be careful that you're substituting in the right values. This one, calculate how much energy needs to be supplied. So again, it's energy transferred again. You shouldn't find any problems with that one. This last one is probably the more challenging one. You're calculating the specific heat capacity, which is C. So remember, we start off with E equals mc delta T. We're trying to work out C, so we rearrange to give this equation. Have a go at it, see what you come back with. Best of luck. Thank you very much, Year 11.